So this is a outline. I will tell the effects of Earth's rotation on the motion of water in the ocean. And for that we need a shallow water equation. I will describe them briefly. Then I will tell about geostrophic balance and quasi-geostrophic dynamics. So for that I will try to go in little bit of detail. So the effect of Earth's rotation is a pseudo force called the Coriolis force, which is a cross product of the angular frequency of the Earth and velocity vector. So this is the velocity of your fluid. So at any given latitude, you can resolve it into components. So the component along the x direction. Okay, before that I should also define a local coordinate system at each latitude. So at each latitude phi, I define my x direction to be the local east-west direction. That is also called the zonal direction, and y direction is the north-south direction, which is the meridional direction, and z direction is the vertical. Okay? So at each latitude you can resolve this f into components. So along the x direction it's 0, the other components are finite. For suppose you are considering some fluid element which is moving along, say, the meridional direction, then you want to consider small deviations around the latitude phi. So for that you need to expand the component of the Coriolis force using a Taylor expansion. So here I am doing that. So phi naught is at the latitude you are in, and if you are considering small deviations around that latitude, this is how the Taylor expansion goes, and you can neglect the higher order terms. And I can rewrite those equations in terms of your y in this form. Now, depending on how much detail you want, you can make approximations to this f. So there are two approximations which are commonly used. One is to use the f-plane approximation, for which we don't consider any variation in the f. So for a given latitude, f is fixed constant. For a different latitude, it could be another constant, but for small excursions around that latitude, we don't consider any variation. So it's essentially a tangent plane fixed at that latitude, and it works only away from the equator, because at the equator this phi naught is 0, therefore the whole expression becomes 0. Now the beta plane approximation is taking one more step in the Taylor expansion. So you have the same f naught plus a component of y, so this is no longer the tangent plane. Now the shallow water equation, these equations are actually simplification of the full Navier-Stokes equation. So what happens is, in the ocean, the extent is, the horizontal extent is very large, maybe thousands of kilometers, but the vertical extent is very small, a few kilometers. And the physical phenomena we are interested in happens much lesser depth. So oceans are essentially shallow water. So what we do is we take the full Navier-Stokes equation, do a depth integration, and get rid of the vertical components of velocity. So here my u is the horizontal component of my velocity in the x direction, v is the component of velocity in the y direction, and eta is a height deviation from a mean height. The mean height is the h naught. G is the gravity and f is the Coriolis parameter.
So now you don't have any vertical component of the velocity.
Yes, correct.
And there's no problem with it. So now the U and V in the plane are no longer incompressible.
It's actually horizontally incompressible also.
So it is still incompressible.
Yes, horizontally incompressible also. Yeah, but this is actually, yeah, so, yeah, yes. So this equation should actually be nonlinear, but I have linearized around the mean field, like V equal to 0, U and V are 0, and the height is a mean height h naught. So I have linearized it. Yeah. Now I will throw away the accelerations to get a balance. So that is called the geostrophic balance, where the pressure gradient is exactly balanced by the Coriolis force. So you get expressions for U and V. Yeah. Now the shallow water equation also can have plane wave solutions. There are two classes of solutions where the frequency is 0 is one mode, which is called the geostrophic mode, and there is another mode where the frequency is finite. It's given by the inertial gravity waves. So it depends on your Coriolis parameter. Okay. Yeah. So quasi-geostrophic dynamics is the evolution of the geostrophic mode, which means the sigma equal to 0 mode. We try to evolve on what happens. So we have to take a few assumptions to do that. So first assumption is that we deal with cases only where the rotation is significant. So which means the scale of the length scale in the problem is large enough. The motion is slow compared to the wave speed, and height perturbation are considered to be small. Now, the original shallow water equation, you try to express it in non-dimensional terms. So this I am showing only for one equation. So I take the first equation and rewrite my variables. I rescale them. Okay. Then I try to identify relevant parameters in the problem. So what I get is 3 parameters, that is a row speed number, which tells me whether the rotation is significant or not, and the Freud number, which talks about the relative speed of these motions, and the gamma, which tells about the height perturbations. Now, according to my assumptions, I want the rotation to be significant, so I choose the Rossby number to be less than 1, and I want the motion to be slow, so I put Freud number to be less than 1. Height perturbations are also small, which means gamma is less than 1, and we take an easier choice, which is to put them all equal to a small epsilon, and the epsilon is less than 1. Okay. Now we rewrite this equation in terms of epsilon, so as this. Now we can expand each of our variable in terms of epsilon. Okay, put it back in the equation and we compare the terms. So this is what. So the lowest order of epsilon in our equation turns out to be 1 by epsilon. So there, if okay, sorry for the typo. So if I balance the lowest order component in epsilon, I get the geostrophic balance back. If I go one step ahead, I can balance the terms at order of 1, and there I get the quasi-geostrophic dynamics. Okay, this is the evolution of geostrophic mode, and essentially it's a filtering of the inertial gravity waves. So this is only for the sigma equal to 0 mode, and in this I have assumed that the F-plane approximation. Okay. Yeah. So you can do it in a beta plane also. Here I am considering a beta plane away from the equator. So there should be a modulus of beta. So there should be a modulus of beta y actually. So this F naught is still large enough. So even if you vary beta y a little bit, it doesn't change anything much. now what you get is a material conservation law from which you can you can linearize with respect to a base state of rest to get some plane wave solution like this, and it's a Rossby wave. Okay, and if I want to do it near the equator, that is the original problem, and then I have some problems. That is the F-plane approximation I cannot use because F is 0. Beta plane approximation is possible, but I still have a problem because this F0 is small, it's very near 0. So beta y, the magnitude could be larger. So I do not know how to solve those. So you can still find a plane wave solution with this frequency, but how to do a QG at this with this approximation, I do not know. So I will stop here.
And what part of this whole talk you have done the calculation?
Okay.
Because they are mostly standard.
Yes. So I haven't done much of my own. I was following the books and the notes. Yeah.
It was not expected that you take everything from the book.
Yeah, I understand.
You have to
Yes.
do some calculation by yourself, so that it will be easy for us.
Yeah, I understand. But a few weeks ago, I didn't know what a material derivative is. A Valis book, yeah.
So one thing I just want to ask you, because saying one, you have the 2 mega sun.
Yes.
So why the sun?
How do you resolve it into components?
Why is sine, not cosine?
Okay. Yeah. Okay. This sine phi is because it's a vertical component, and that is what matters to us because our fluid moves in the horizontal plane. So.
Can you just simply draw a little bit and explain?
Yeah, sure. So this is where you are, and so the direction of omega is its rotation is this, and if you want to resolve it into components, then in the horizontal plane, so in the x direction which is going in, it becomes 0, and you have two components. One is to the local north, and this is cos phi, and this is sin phi. And your equation has a term, okay? And because this u is only in, the component which matters here is.
No, the component which is cos phi won't matter.
No, because you have motion in this direction, so the cross product will cancel out.